Basically, there are three types under the system, that is open system, closed system and isolated system. Under thermodynamic properties, we have two main properties, that is intensive and extrinsic properties. The absolute value internal energy cannot be measured, but the change in internal energy can be measured. In isothermal process, the temperature remains constant, therefore delta U is equal to 0. Hello dear students, I am Roja, your chemistry lecturer from Vidhyaashram PU College, the Temple of Excellence, Mysuru. So today we are going to start a new chapter, that is thermodynamics. So in this session we are going to study about thermodynamics, then thermodynamic properties, first law of thermodynamics, expression of mechanical work done in isothermal reversible compression of gas, and also about concept of enthalpy. So what do you mean by thermodynamics? Thermodynamics is a branch of chemistry that deals with the study of flow of heat, that is energy changes in a process. So there are two terms basically we need to concentrate on, that is system and surrounding. So what do you mean by the system and surrounding are? So the system is any specified portion of matter or universe under the study is called as system. So basically there are three types under the system, that is open system, closed system and isolated system. So under open system, a system which can exchange both energy and matter with its surrounding is called as open system. That is, for example, water in a open container. So it's not a closed container, just kept water in a container. So that is called as an open system. And in the closed system, a system which can exchange only energy but not matter with its surroundings is called as closed system. So here the system is closed, that means water is kept inside the container. There is no exchange of matter, it's only the matter is kept inside. So it is closed system. Then there is an isolated system, that means a system which can exchange neither energy nor matter with its surrounding is called an isolated system. Example, water in a thermos flask. So neither energy nor a matter is going to exchange. So it is being there in the container as such. Now what do you mean by surroundings is? Surrounding is a portion of matter which is excluded from the system. That means part of universe constituents are considered in the surroundings. So and are capable of exchanging energy and matter within the system. So such is called as surroundings. So let us know about thermodynamic processes. What are the processes that comes under thermodynamics? So when the thermodynamic system changes from one state to another, this operation is called as thermodynamic process. So there are two types in the thermodynamic process, that is adiabatic process and isothermal process. Here in adiabatic process, it's a process in which no heat is exchanged between the system and surroundings is called as adiabatic system. Example, the reactions carried out in an isolated system. So isolated system, we know that there is no exchange of heat or matter in the system. In isothermal process, iso in the sense it is same, thermo is heat or temperature. So in this system or in this process, it's in process in which temperature remains constant. That type of process are called as isothermal. Example, the reactions carried out in a thermostat. So there are some other processes that includes in a thermodynamic process. The other one is isobaric process. Baric in the sense it's meaning a pressure. It's a process in which pressure remains constant is called as isobaric process. Example, the reactions that is carried out in an open system. So in that pressure remains constant. Then next one is isochoric process. Choric in the sense it's about volume. Here it is a process in which volume remains constant, so it is named as isochoric process. Example, the reactions carried out in a closed system. So the next one is reversible process under thermodynamic process. So therefore it is a process which can be reversed at any instant of time and equilibrium exists between system and the surrounding is called as reversible process. Example, electrochemical reaction in a Daniell cell. Then irreversible process is about a process which cannot be reversed at any instant of time, and equilibrium does not exist between system and the surrounding. So such type of processes are irreversible. Example, heat flows spontaneously from a hot body to a cold body. So it cannot be reversed. So the next topic is thermodynamic properties. Under thermodynamic properties, we have two main properties, that is intensive and extensive properties. So extensive property means it's a property which depends on the quantity of matter. Such type of properties are called extensive property, that is present in the system. And therefore, example are mass, volume, enthalpy, entropy and internal energy. So intensive properties are, it's a property which does not depend on the quantity of matter present in the system, and therefore which are those which includes in the intensive properties are temperature, pressure, boiling point, surface tension, etc. So next is about internal energy. It is the sum of different kinds of energies possessed by a system is called as internal energy. So the components of internal energy are potential energy, kinetic energy, rotational energy, vibrational energy, bond energy as such. The absolute value internal energy cannot be measured, but the change in internal energy can be measured. That is delta U. Delta U represents, that is change in internal energy. Internal energy is represented by U. So delta U represents change in internal energy is equal to U2 minus U1. So U2 is nothing but final energy, U1 is initial energy of the system. So next topic is about first law of thermodynamics. So it states that energy can neither be created nor be destroyed, but it can be changed from one form of energy into another form. So this is called as law of conservation energy also. So the mathematical representation is delta U is equal to Q plus W, and the mathematical form of first law of thermodynamics is given by as such, that is work done on the system is given by as such. Now consider a process, that is A changes to B. Now internal energy of the system of A is equal to U1, and then amount of heat absorbed in the A system is Q, and the amount of work done here is represented by W. Next is total energy of the system is given by U1 plus Q plus W. Then internal energy of the system, that is B, is given as U2. Then U2 is equal to U1 plus Q plus W. Therefore, U2 minus U1 equate the equations. Now, U2 minus U1 is equal to Q plus W. Therefore, change in internal energy is given by, that is delta U is equal to Q plus W. So, this represents the first law of thermodynamics. So, next is how is mechanical work done in an adiabatic process. So, in adiabatic process, no heat is exchanged between system and the surroundings. So, therefore, the equation Q is equal to 0. Then work done by the system, that is W is given as is equal to minus delta U. Then work done on the system is given as delta U. Therefore, the expression for mechanical work done in an adiabatic process is given by W is equal to minus NCV into T1 minus T2, that is depending upon the temperature. Now, mechanical work done in an isothermal process is given by as such, that is in isothermal process, the temperature remains constant, therefore delta U is equal to 0. Now, work done by the system will be W is equal to Q, and work done on the system will be W is equal to minus Q. Therefore, the equation is given as W is equal to minus 2.303 nRT log to the base 10 V2 minus V1, or if it is expressed in terms of pressure, W is equal to minus 2.303 nRT log to the base 10 P1 by P2. So, that is the equation to represent the mechanical work done in an isothermal process. So, now let us see how to derive the expression of mechanical work done, especially in isothermal reversible compression of a gas. So, let us consider a cylinder which contains 1 mole of gas. So, in a cylinder we have to take 1 mole of a gas fitted with frictionless piston. So, there is a piston over here. Then The total volume of the gas will be represented by VI, that is volume at the initial stage. So pressure of the inside gas is represented by P. Then external pressure, that is what we are going to apply through the piston, is given by PEX, that is P represents pressure, external pressure. So therefore the external pressure will be greater than the pressure of the inside gas. On continuing this, as a result, piston moves inward till where? Till the pressure of the inside gas becomes equal to the external pressure. During this compression, piston moves a distance L and area of cross section is represented by A. So volume change is equal to L into A is equal to delta V, that is change in volume, is given by Vf minus Vi. Vf in the sense volume at the final stage, Vi is at initial stage. Now but we know that pressure is given by force by area. So therefore force in the piston is equal to pressure into area, which is represented as external pressure into A. If W is the work done on the system by the moment of the piston, then work done is equal to force into distance, which is given by external pressure multiplied by area cross section multiplied by distance. So therefore, to this equation we will represent delta V. Then work done is equal to PEX minus delta V. So on multiplying we get minus PEX delta V. Then instead of delta V, we can apply this value. So therefore, work done is equal to minus PEX. So instead of delta V, we can also assume it is into Vf minus Vi. During compression, so final volume will be lesser than the initial volume. Hence, W becomes positive, which indicates work is done on the system on integrating equation 1. So we are going to integrate the equation 1. Therefore, the equation becomes W is equal to minus integration to Vi to Vf, that is P external dV. So this is the integral form of the previous equation. During compression, external pressure will be greater than the internal pressure. So pressure increases and then during expansion pressure decreases. Therefore, external pressure is equal to internal pressure plus dP in compression, and external pressure is equal to internal pressure minus dP in expansion of gases. So on applying that in general, external pressure is equal to internal pressure plus or minus dP. So we will apply the same thing here. A work done in a reversible process is equal to minus integral to Vi to Vf, P external dV is equal to minus, so internal pressure plus or minus dP to dV. So this can be solved and rewritten as such, that is integration to Vi to Vf minus P internal pressure dV plus or minus dP dV. Then in a reversible process, the system is at equilibrium. Therefore, since dP into dV is very small, we can write the equation as the work done in a reversible process is equal to minus integration to Vi to Vf internal pressure into dV. But PV is equal to nRT. This is the ideal gas equation. So therefore, pressure is given as nRT divided by V into dV. So we will apply the same thing here in the previous equation. Therefore, the equation becomes minus integration to Vi to Vf nRT by V dV. So why do we have to take nRT is they are constant. So here volume of the gas will change. So therefore, W is equal to minus nRT log to the base E Vf divided by Vi. And therefore, this equation continues here as such. Now, work done is equal to minus 2.303 nRT log to the base 10, that is Vf by Vi. We know that P1 V2 is equal to P2 V2. Therefore, P1 P2 is equal to V2 V1. And then on applying in place of volume, the pressure, so we get the equation W is equal to minus 2.303 nRT log to the base 10, that is P1 by P2. So this is the equation for the mechanical work done in an isothermal process. Next, we'll move on to types of reactions, that is exothermic and endothermic reaction. So exothermic reaction are those in which the reaction in which heat is liberated or evolved is called as exothermic reaction. Example, When carbon reacts with oxygen, it gives out carbon dioxide, leaving out gas or a heat. Therefore, heat change is given by minus 303.5 kilojoules. And in the second reaction, that is when hydrogen reacts with oxygen, it liberates heat, so it to form water. Therefore, the change in heat is given by minus 285 kilojoules. So, minus represents that is exothermic reaction. Now, when it comes to endothermic reactions, the reaction in which heat is absorbed are called endothermic reactions. For example, so when carbon reacts with sulfur, it gives carbon disulfide. So, heat changes given by minus 117 kilojoules. And when it comes to the other reaction between nitrogen and oxygen, it gives nitrogen oxide. So, therefore, it is given by plus 108 kilojoules. So, next topic is thermochemical equation. So, thermochemical equation is the balanced chemical equation which indicates the physical state of reactants and products and also indicates heat changes in the chemical reaction. So, for example, carbon on reacting with oxygen gives carbon dioxide, liberating energy of minus 393.5 kilojoules. So, if it is expressed in terms of mole, so we can say that when 1 mole of carbon solid combines with 1 mole of oxygen gas, it forms 1 mole of carbon dioxide. Looking into the balanced equation, we can represent this in terms of mole. So, in this reaction, 393.5 kilojoules heat is liberated. Now, if it is expressed in terms of mass, so it is when 12 grams of carbon solid combines with 32 grams of oxygen gas, it forms 44 grams of carbon dioxide. So, during this reaction, again 393.5 kilojoules of heat is liberated. Next is about concept of enthalpy, which is represented by H. Enthalpy of system is defined as the total heat content of a system and is measured as the sum of its internal energy and the product of pressure and volume. So, mathematical representation is given by H is equal to U plus PV, where H is enthalpy, U is internal energy, P is pressure and V is the volume. So, this is the relationship between enthalpy and the internal energy. So, what happens when the enthalpy is changed? So, it is represented by delta H. Therefore, the equation is turned out as delta H is equal to H2 minus H1, where delta H is represented as change in enthalpy. H1 gives initial enthalpy and H2 gives final enthalpy. So, in a chemical reaction, the change in enthalpy can be written as delta H is equal to Hp minus Hr, that is change in enthalpy of a product minus change in enthalpy of a reactant. So, therefore, we will term this equation as 1 and this equation as 2. So, the equation 1 and 2 are the energy equation used in the thermochemistry. So, note, in a reaction, if Hp is greater than Hr, then change in enthalpy will be positive. So, it represents the reaction as endothermic. If Hp is less than Hr, then change in enthalpy will become a negative. So, the reaction is exothermic. So, for a change in enthalpy at constant pressure, we can also write it as delta H is equal to delta U plus P delta V. That means there is no change in pressure. So, for that the equation is as such. So, let us move on to the next one, that is relation between change in enthalpy and change in internal energy. So, it is given by the equation delta H is equal to delta U plus RT delta N, which is in of a gaseous state, where delta H is equal to change in enthalpy, that is heat of reaction at constant pressure. Then delta U is equal to change in internal energy. R is a gas constant, then T is the temperature in Kelvin. Then delta N, which is of a gaseous state, is equal to number of gaseous moles of products minus the number of gaseous moles of reactants. So, that is delta N. So, next is about heat capacity. Now, heat capacity is the measurable amount of heat required to change the temperature of the substance by 1 Kelvin. So, the amount of heat required to raise the temperature of the substance by 1 Kelvin is called as heat capacity. Now, what is molar heat capacity is? Molar heat capacity is represented by Cm. So, molar heat capacity is defined as the amount of heat required to raise the temperature of 1 mole of a substance by 1 Kelvin. So it is represented by an equation, that is molar heat capacity is equal to C by N. C is nothing but heat capacity divided by number of moles of a substance. Next is specific heat capacity. It is represented by small letter c. So it is defined as the amount of heat required to raise the temperature of 1 kg substance by 1 Kelvin. Now, to find the heat required to increase the temperature of any substance, the following formula is used. The formula is Q is equal to C into M into delta T, that is heat absorbed is equal to specific heat into mass of the substance into temperature change. So, therefore, if mass of the substance is 1 kg, then C into M becomes C. If the same thing is applied to the equation becomes Q is equal to C into delta T. So, this gives the specific heat capacity of that substance. So, next is about relationship between molar heat capacity at constant pressure. So, it is represented by Cp, and Cv, that is molar heat capacity at constant volume, or this can also be called as, to derive Cp minus Cv is equal to R. Now, how to derive at the equation Cp minus Cv is equal to R? Let us go through. So, therefore, the amount of heat of a given system depends on the mass of the substance, that is M, and increase in temperature of the substance, that is delta T. So, therefore, for a given substance, Q is directly proportional to M, that is mass, and also Q is directly proportional to change in temperature delta T. If these two equations are put together, it becomes Q is directly proportional to mass and the change in temperature. So, if the proportionality constant is removed, then we will have to add a constant with equals to. So, therefore, the equation becomes Q is equal to Cm into delta T, where this C is nothing but a constant. If mass of the substance is 1 mole, then Cm becomes C, that is molar heat capacity. So, therefore, equating the same on the previous equation, we get Q is equal to C into delta T. Let we consider as one equation. Then at constant volume, QV becomes Cv delta T is equal to delta U, which we will consider as equation 2. At constant pressure, that is Qp is equal to Cp delta T is equal to delta H. So, this will consider as equation number 3. Now, for 1 mole of an ideal gas, delta H is equal to delta U plus delta RT. So, now we will substitute the equation 2 and 3 here. Cp delta T is equal to Cv delta T plus delta RT. Now, Cp delta T is equal to Cv delta T plus R delta T. It is the change of temperature, not the gas constant. So, in the next step, we are taking delta T as a common. So, the equation becomes Cp delta T is equal to delta T into Cv plus R. Now, Cp is equal to Cv plus R, that is because change in temperature is eliminated. Then, therefore, the equation becomes Cp minus Cv is equal to R. So, here delta T and delta T becomes equal. Therefore, Cp minus Cv is equal to R. Thus, the difference between molar heat capacity of a gas at constant pressure Cp and at constant volume Cv is equal to the gas constant R. That is 1.987 calorie per mole per Kelvin, or 8.314 joules per Kelvin per mole. So, that is how to derive the equation Cp minus Cv is equal to R. R is a gas constant. So, that was about today's session. So, in the next session, we shall learn about law of thermochemistry, then enthalpy change, that is delta RH of a reaction enthalpy, then enthalpies of different types of reactions, then spontaneity, also about Gibbs energy change and equilibrium. So, thank you.